Hi, this is Dr. Nick from the ECG Academy with Chapter 2 in this basic section of electricity. We're going to talk about electrical circuits, and don't worry, you don't need to know this whole ugly looking circuitry thing, but I am going to talk about some basic ideas, some concepts in electrical circuitry, because after all, electrocardiograms are recorded by electrical instruments, and you kind of have to know a little something about what you're dealing with. So let's get rid of this horrible thing. But between you and me, my favorite place to hang out when I was in high school was Radio Shack. Oh my God, my soldering iron was my best friend. Just kidding, but maybe not. Anyway, we're going to get rid of this circuit and we're going to talk about movement of electrons. This is what electricity is. And, we sort of talked about a wire and electrons moving through a wire. So you can imagine all these electrical charges that are somehow able to move in a circuit. Well, what's going to push them, though? How can electrons move around in the circuit and there's nothing there that pushes them? Well, in a normal electrical circuit, we have some kind of push to the electrons, and that's what we use batteries for. So a battery is basically a source of electricity because what it does is it takes a chemical reaction and converts it into electrical energy that allows electrons to get pushed out the negative pole, and that provides the force to allow electrical currents to move. When we draw electrical circuits, we use special signs or symbols to represent different electrical components, and a battery is generally drawn with a symbol that looks like this. That just simply means a battery. Now, the smaller line is always represented. You can remember the small line looks like a minus sign, so that's the minus sign, and this is the plus end of the battery. And if you imagine a wire that leads in a circle, okay, this would be an example of an electric circuit, where the electrons are pushed out the negative end and they flow around in a circle and they return to the positive end. Okay, so that's the most basic kind of circuit. Of course, if you just simply connect a wire from one end of the battery to the other, the battery would just get used up. It would turn hot because heat is evolved in the chemical reaction. So let's think of something a little bit more interesting than just a wire. So we'll start with our battery, and then we'll let this electrical current do some work. Let's say we attach it to a light bulb. That's right. So a light bulb is generally drawn look like this because it kind of looks like the filament in a light bulb. You know how a light bulb looks like this? Well, that little loopy thing represents the filament. So now you connect the circuit, and so electrons flow out and they go through here, and as they reach the light bulb, it, lo and behold, causes the light bulb to glow. So a light bulb is something that does work, and generally things that do work create some kind of resistance for the electrical current. So you want to draw it as a different type of circuit, you can just draw this as a resistor, which is some kind of resistance. And then when we talk about the human body, sometimes we're applying electrical energy to the human body, and the body itself acts as a resistor. So here's a simple circuit. If we just let this current flow, of course, what will happen is the battery eventually will drain, and it's not very interesting. So there has to be some way to sort of stop and start the flow of electrical current, and that's what switches are for. So if I were to just sort of like interrupt this circuit here, now, of course, you have a break in the circuit. It's called an open circuit for those electricians out there. But we have to be able to close this circuit when we want to. So the electrical symbol for a switch has two little dots there and a line that represents sort of like a push button or a switch, so that this line can then close, if you want, to allow the circuit to flow. So when the switch is closed, then the electricity flows the way it's supposed to. And then when you open the circuit by opening this switch, then the circuit stops. That's all well and good, but how do we actually measure what's going on here? Well, there are a bunch of electrical components that can be used to monitor how much current is flowing. And if you imagine sort of some kind of a meter that would measure this electrical current. We would actually represent this as a circle with a V, and that's like a voltmeter, because the amount of force that the battery provides in moving the electrons around in a circuit is measured in volts. So a 9-volt battery has a lot more force than a 1.5-volt battery. So the voltage describes how rapidly these electrons are flowing around the circuit. And, voltmeters can look like anything from like a cute little meter, da-da-da-da-da, that the needle bounces when the voltage goes up. But when we're recording electrocardiograms, what we use is a kind of a voltmeter, but it's turned on its side. And instead of a needle, it uses a pen or some electronic equivalent of such, so that when the needle bounces back and forth with the variations of the voltage, it draws a line, and that gives us the squiggles that we commonly look at and reading a cardiogram. So imagine an ECG machine is kind of like a voltage meter, a voltimeter, or a means of displaying on paper, or of course on a screen if you're looking at a cardiac monitor, the variation in the voltage that's flowing around the circuit being, of course, the human body somehow. And we're going to talk about how electrical signals are in fact recorded, what the different kind of recording systems look like, and it'll give us a sort of a basis to understand the concept of an electrocardiographic lead and how we use different leads to determine what direction voltage is going in. Because when the heart beats, it produces voltage that actually has a direction. And we'll talk a lot more about that in the next video. Thanks for watching.